The laser, while not a new product, is a new technology. We've had this out since the late 2013 and continues to amaze all of us, especially me. I work with lasers all the time, and the laser is just continuing to, we're finding applications where it will work where other products won't. So we want to share those with you and make sure everybody's up to speed on what we're capable of doing. We're going to do a quick review of area velocity basics. We're also going to do a review of the non-contact laser velocity measurement theory, so everybody's up to speed on that. We're going to do a review of some third-party accuracy data. We've proven now that the laser is very rugged, can handle a lot of extreme conditions, and the next phase is kind of how accurate is that device. We've done a lot of testing comparing to other standards in the industry, but we've also done now a lot of third-party lab testing. We want to share that with you as well. We're going to talk about some applications. It's all about how you measure flow in some of these applications. What you've been using in the past may not work, and so you're scratching your head, how do I get an accurate measurement on some of these difficult applications? And I'm going to share with you how laser will help you in some of those conditions. So hopefully you'll get a lot out of this today, and we're again excited to have you. This is a photo of the Isco Flow Measurement Laboratory. One of the things I think that we have a huge advantage over other manufacturers out there is this facility. What this is a, again, flow lab. We can go 4-inch to 24-inch pipes. What we use this for, though, is design, development of new technologies, but we also use it for continuous improvement and evolving our technologies. Laser is no different. We came out with the laser, again, several years ago, and we continue to evolve and improve how it performs, and this lab has certainly helped us do that. If you do take a vacation to Nebraska, we'd be happy to have you. Give us a holler and we'll give you the tour. Okay, let's do a quick review of area velocity flow measurement techniques. Q is your flow is equal to the area of that flow times the velocity. To get the area measurement, we do a level measurement. And typically, we use a pressure sensor. So those of you that are familiar with 2150s out there, we use a pressure sensor, but there are also ultrasonic sensors. In the case of laser, that's what we use to get our level measurement. We use, for our velocity component, we use a Doppler technique. There are some others out there, electromagnetic, but for the most part, Doppler is the predominant one in the industry. There are different types of Doppler velocity measurements. Some are called contact sensors, and some are non-contact. 2150 contact sensor would be one that's mounted on a ring in a pipe, and the non-contact, of course, would be the laser. This is kind of a good little artist rendition of what we're talking about. This is a continuous wave area velocity sensor mounted on a ring in a pipe. And to get the flow, we need the level. We use a pressure sensor to measure the water depth. We use a continuous wave Doppler sensor technique to measure the average velocity of the flow. So these work very well, been out there forever, the workhorse of the industries, but they do have some limitations to how effective and accurate they are as you get into deeper and deeper flows. All right, so let's talk about some applications that you might see in the industry out there. We design for collection system, although we are more and more involved in wastewater plants as well as water plants. But initially, laser was designed for collection systems. We designed them for large pipes. We've defined large pipes. Anything greater than 36 is definitely a large pipe. And small pipes, we find more and more applications all the time now where people are trying to measure flow in pipes smaller than 36 inches, a lot of times even as low as 6 and 8-inch pipes. So some applications we're going to talk about. The one on the left, you'll notice, is a large pipe, very dangerous. Don't want to get in that flow if you can help it. But again, the one on the right is more and more residential or private property I&I monitoring that we're seeing out there. Okay, so one thing we think we have done a pretty good job of is we came up with LaserFlow, and we feel that that truly is one of the keys to unlocking a successful monitoring program. However, with any application, we want to look at what your goals are, what the application is, I want to make sure we provide the right product for that application. So our field support people, our sales reps in the industry are probably the most trained in the world. They are very knowledgeable about product technology as well as applications. So they do a great job for you. We also have internal staff that are in our product support group, and they also have a great deal of knowledge and expertise in these areas. Bottom line is we want to provide the product that's going to best suit you in your application. We've always said not one size fits all. That's still true today, but I will say the LaserFlow is proving to be the closest thing that I've seen in my 30-plus years of doing this to the one size fits all. Nothing's perfect, nothing fits every application, but the laser is about as close as it gets at this point. Okay, so let's talk about the laser. Theory of operation, I'm going to go into more detail with this individual components, but as an overview, what we do is we have an ultrasonic sensor that's mounted in the back of the laser. It transmits a sound wave, reflects off of a 22.5-degree deflector molded on the side of the, or in the back of the laser. We know where the water depth is. Once we know where the water depth or water is, we know where we want to take our reading. We focus the laser below the surface of the water. This is key, and part of the patent of the laser is subsurface velocity measurement. There are other, I would say, me-too kind of products out there that do non-contact velocity, but all of those are surface velocity. Laser is the only one that actually goes below the surface to get the velocity reading. Before we get into the laser velocity, let's talk about the operation of the ultrasonic sensor. One thing that we try to do here at Teledyne Isco is really look at what is currently available in the market, things that people do right, and maybe areas that we can improve. One of those areas was the ultrasonic sensor. And you have both the velocity measurement as well as level. So what we did on the ultrasonic sensor was we heard comments that if the sensor is mounted straight up and down, you could have condensation that can cling to the face of the sensor. What we did on the laser design is we went in and we put that sensor in the back of the sensor housing, and we angled it. What that does is any moisture in a manhole, which we know is common in a manhole environment, will drip right off the edge of that sensor and not cause a problem. Also, if that sensor does go underwater, it will just run right off once the submergence goes away, and away we go with our level measurement. Again, we shoot off that deflector plate. One other thing that we've done is we've done a pretty good job of looking at a deadband. What a deadband is a blanking distance from the ultrasonic sensor face to a known distance. In the industry, it's very common to have a 12-inch deadband. We have one in this sensor. So what we want to do is we want to minimize that effect, and the way we've done that is by putting the laser in the back of the sensor, the ultrasonic in the back of the laser sensor, and now we take into account that 12-inch deadband in the body of the sensor itself. For that reason, we now have virtually a zero deadband ultrasonic, so water can go all the way up to the bottom of the laser before it will not read level. We have a range of 0 to 10 feet. So for 98%, 99% of the applications we deal with, this handles that range quite well. So we don't care if it's a foot away or 10 foot away from the flow. All right, so that's the ultrasonic level sensor, and again, been very, very successful for us. Let's talk about the laser itself, though. A laser pointer has a constant focal point, which means our focus point goes on and on pretty much in infinity. The way the laser works, though, is we need to focus that laser signal or the laser beam into a known point so that we can get a good representation of the water velocity. So what we do is we know where the water surface is. We know where we want to focus the laser. We basically will move the laser until we get the smallest point or the tightest focal point on the laser beam. What that does for us is that gives us the maximum intensity or signal energy back to the laser beam. Like any Doppler device, we transmit a known frequency, and based on the frequency return or the frequency shift, we can calculate the direction and the magnitude of the velocity reading. So to give you another kind of idea, another look at what this does, laser knows the water level, knows where it's at. Once it knows where it is, we focus the laser below the surface. This is a little exaggerated, but if you did stick your hand under the laser when it's in operation, you'll notice that the size of the laser beam coming out of the laser is about the size of a coin. Where it focuses the laser, though, is a very tight laser-like point, which you should see. This is, again, below the surface of the water and known as the converging section or point of convergence, which is key. This is where we want to look for our velocity readings. What's amazing about this is we take 5,000 spectral velocity readings. We do this in roughly 2 seconds. By comparison, and again, going on the concept of continuous improvement, Laser 1, which was released in early 2014, took about 40 to 45 seconds to do the 5,000 velocity spectrum scans. The firmware's been updated and improved, and now we do all of this in again, 2 seconds. So a lot of improvements have taken place since the early release. So some of you that may have worked with laser early on, you'll notice a distinct difference in some of the performance of the new laser. Okay, this is really what it's all about. Is this here is the velocity spectrum. So if you look at my cursor, what you can see is zero velocity. To the right is the frequency or the speed of the water. This peak right here is what we're really looking for. This is made up of those 5,000 velocity scans. The more of those 5,000 that agree on that frequency, the more area under the curve and the better looking this signal will be. This is very key in setting up a laser as well as post-processing laser data. When I look at this, I have no question we are getting a very good velocity reading at that location. So these are known as velocity diagnostics. We are a little bit overkill sometimes on velocity diagnostic. Everybody can give you a nice pretty line and a nice pretty graph. What we are really key into is how good is that number. And again, the velocity diagnostic help you determine that. Okay, so this is another snapshot of what you will get from the laser. So one of the reasons we're able to read, and I'm going to go through this in more detail, but clean and slow water is the signal-to-noise ratio. Any Doppler device, whether it's a sensor in the water or a laser, it's all about the signal-to-noise ratio. The laser has incredibly clean signal compared to the noise. So that's what we're looking for right there. That is our return spectrum made up of 5,000 velocity readings. This is the noise floor. As we go towards the left, towards zero, that is zero velocity. Laser vintage 1, 4 years ago, 3.5 years ago, that noise floor was considerably higher. What that meant was the minimum velocity we could read then was about 0.8 feet per second. We can now read down to our new specified 0.5 feet per second. In some cases, we'll read even slower than that, and actually a lot of cases. So it's all about signal-to-noise ratio. Some of the engineers were able to figure out some things. They cleaned up on the electronics and now improved, again, the new laser that you would buy today. This is really a measurement of the quality of the velocity reading. It's also a value that we quantify as what's called Doppler power, and it's stored in the memory. When you graph that Doppler power, the value we're looking for is anything greater than 1,000. As long as we have 1,000 or higher Doppler power, we know we are getting a sufficient amount of return from that spectrum, and we like what we see. This is very, very key information. It's like an MRI, as corny as that sounds, when you're looking at laser velocity reading. Okay, so that's how the laser does both level and velocity. Let's look at how we can set this thing up. This is a theoretical velocity profile. In a uniform flow, you would have peak velocity normally below the surface in the middle of the flow channel. Due to Piper's friction, as you move to the outer layers, it will slow down. So the laser can be set up. It reads the level, knows where the water is. Once it knows where the water is, it can then start taking its velocity readings. So what it's able to do is actually scan horizontally 5 points as well as vertically 3 points. This is known as a multi-point, multi-depth velocity method. So the laser is very, very unique in the fact that it can go ahead and take readings from multiple points throughout the channel without being in the channel or the flow. Each one of those, again, keep in mind, is 5,000 velocity readings. So if you do the math, you have 15 points, you really are taking about 75,000 velocity readings, and it does all that in roughly a minute and a half. Okay, so I often get questioned, why wouldn't I do all, or when would I do individual ones? And really it comes down to power. How am I going to power this thing? Is it remote? Am I on batteries? AC powered? Is it billing? How fast do I want readings? All those come into play. So if it's a remote location, what I'll do is I'll turn all 15 on, see how uniform my velocity is. If things look fairly uniform, a lot of times I'll just put 2 on. And the reason I do 2 is so I have a second opinion. If something comes floating by at the time it takes one reading and gets a bad reading, I want it to have another chance of getting a good reading. But this is completely user definable. All right, so let's talk about accuracy. We've done a lot of field testing in the marketplace, and these are all really customer tests, and we've done these and had incredibly impressive results. Some of the standards they've been compared to, as you guys are all familiar with, flumes. Flumes have been out there forever. Flumes are traditionally expected to be roughly a 5% accurate device if they're installed correctly and all conditions are right. What I'm finding is that flumes are not always right, and just because you pull out your Isco handbook and you look at the level reading and it did the math right doesn't necessarily mean the flume is right. So more and more lasers will be used to verify the accuracy of flumes, but flumes have been compared to laser over the past several years. Magnetic flow meters, another one that's popular out there. Obviously, mag flow meters need a full pipe for the most part, but we've been compared to a lot of those mag meter applications as well. Acoustic Doppler, or ADFM, range-gated Doppler. For those of you that have been doing this for a while, MGD might come to mind. These are pulse Doppler devices that measure a velocity profile through the channel. So we've been compared to those as well. We sell those or offer those as a product, and the laser is compared very favorably to that technology. Transit time, or multi-path transit time, there are multiple sensors in a pipe that measure the velocity distribution as well. Also considered to be a very accurate standard, and we did quite well with those. You have weirs out there. Weirs have been around since the dawn of time. We know a level reading. We know the shape of the weir, and we can calculate the flow. Again, roughly a 5% devices. And then there are dye dilution tests that have been done compared to the laser as well, and it's done very well in every one of these comparisons or standards. Okay, so then you finally get to, well, we want to do some, how do you do against the lab? Let's do some lab testing, and let's see how we do. This is kind of an interesting photo. I thought I'd throw that up there. It's actually showing 2 laser points, but in reality it's one. You'll see the top one's hitting the water, and the one at the bottom is actually hitting the bottom of the channel. Okay, so accuracy. Our current published specified accuracy is 4% of reading, which I should mention is the most accurate non-contact velocity or flow spec in the industry. We have done, again, third-party test results. What we've found on third-party test results, we've done some testing with a facility called the Irrigation Training and Research Facility in Cal Poly San Luis Obispo, California. They are very well respected and known in the industry out there on the West Coast. We were felt to be at about 1.8% absolute error, so did very, very well in their testing. And we also went to the East Coast, and there's another facility called the Alden Research Lab. Alden is another very well-respected flow lab on the East Coast, and a little different setup there. We were 2.7% absolute error. So in addition to all the field testing that have been done, we now have third-party results that support the accuracy of the laser. So well within our 4% spec. Okay, so let's talk about some difficult applications. There are many out there, and we're finding more and more all the time. High velocity, low level is a common one. Where you find those are in, steep slope pipes. since the laser came out, I'm amazed at how many of these types of applications we run into these days, and I'm going to talk about how we're able to overcome some of these challenges. Low-level raw wastewater applications. And what I'm referring to are just standard wastewater applications where the flow depth is less than 1 inch. And for those of you that have been doing this for a while, you'll know, and you know that you normally need about 1 inch or greater in order to get enough water to cover the sensor. So that becomes a challenge if you want to measure flows in those types of applications. So slow velocity, another one. This is a challenging thing. And when I talk slow velocity, I'm talking anything less than roughly half foot per second. Okay, 2150s. For those of you that have those out there, we have a lot of sites where we can read below half foot per second with a 2150 with good results, or very good results. The laser spec now is a half foot per second. In many cases, we run into sites that are much lower even than that, and the laser will work quite well. We find these a lot in residential collection system, and we're seeing a lot more private property or personal property I&I studies that are going on, and you have some of these applications. Slow velocity also has a tendency to silt over a sensor, so it becomes a challenging thing if you have a sensor on a ring in the pipe. Slow and clean applications, and I'm talking about wastewater effluent, sometimes not necessarily slow, but it's going to be very clean. Chlorine contact or UV disinfection channels. These are another part of the application market that we are becoming more and more involved in. People want to measure the chlorine contact chambers and UV channels, and there's nothing out there that's been able to do that effectively until laser. Drinking water plant effluent. We have more and more applications where not only dirty water, but clean water. They want to measure what's coming into the plant. The water tends to be fairly clean, and a traditional sensor, a lot of times, will have a difficult time measuring that. Stormwater monitoring, not going away, seems to be picking up. And stormwater challenges are wide fluctuation in flow conditions. So you have maybe very low flow or no flow, and you could have a raging rapid when things happen. So those are challenges. Irregular shaped channels. Almost all stormwater lines, unless they have a good defined circular concrete culvert, will run into some irregular channels. I'm going to show you how we can deal with those as well. So these are some of the applications we're going to talk about today. So high velocity challenges with traditional flow sensors. What's the problem with that? Well, you have what we would call kind of a rooster tail effect over the sensor. The water literally flies over the top of it, which creates kind of a cocoon effect, which will tend to make a sensor read a little bit lower than it should for level. It's also difficult to accurately calibrate that level. That water's moving through there 4, 5, 6 feet per second. As you know, sticking a ruler in there is not a fun experience, and it's very, very difficult to calibrate. When we have that much stuff coming at a sensor, an area velocity sensor, you have a lot of entrained air, you have a lot of particles moving at very high velocity, can tend to make the sensor slightly nearsighted. So can affect the effective, really overall accuracy of the velocity due to some of the noisy water hydraulics. And as you know as well, difficulty in installing a mounting band. The people that I've talked to out there that do this for a living have told me as a general rule, if it's 3 feet per second or greater, it's going to be very, very difficult, if not impossible, to install a ring, as well as being extremely dangerous. Nobody wants to be in flows with those types of conditions. This is kind of a neat shot I liked. It was from a lab in Europe, but you can see just the hydraulic effect of high velocity over a sensor that's in the flow stream. Okay, this one was a good photo. It's a little difficult to see, but if you can look up in there, what you'll notice is way up before that first pipe connection, the flow is very uniform hydraulics. Once it gets closer, it hits that first pipe joint and then the ring, you'll notice we start getting very turbulent. What's going to happen is you're going to have errors in both level as well as the velocity readings, and then your cable is going to come loose from the band eventually due to high velocity. All cables used or cable ties, are not going to last forever. So in the case like this, if it's a long-term planned, then a good chance it's going to come loose, you're going to catch debris and all those things. So any contact sensor could suffer from these types of things. So let's look at another application. This is a low-level, high-velocity application. Level is, in this case, below an inch. The specification for the laser right now is we can read velocity down to a ½ an inch per our specification. Having said that, we have cases where we've read actually much lower than even a ½ an inch. Our velocity is 15 foot per second, so we can read all the way up to 15 foot per second. So this is a high-velocity billing application. They decided there's no way you could put a in-pipe sensor in there due to both the hydraulics, the depth of water, and the velocity. So what we did is went ahead, they bought a laser, 2 bolts hold it in place. It makes it very easy to install in this location. It should be noted that the laser can be installed both upstream and downstream. It doesn't care which direction, and it can read bidirectional flow. So very, very capable technology. It has also a built-in accelerometer, so it knows its X, Y axis. So when they install it, you can tell exactly where that laser is positioned. X is 0 ± 3 degrees, Y is 45 ± 3. The Y angle can affect the accuracy of the velocity reading. What's unique about laser is that it knows where it's physically mounted. So if the install is not exactly perfect, it will compensate for that error with the built-in accelerometer. So it even further tunes your accuracy. Okay, so here's another site that was a high-velocity billing location. This one happened to be a closed pipe. They did not really have an open channel here like a normal invert. Well, what they were able to do is just make a small cut in the pipe. So they have a round pipe coming in. This one happened to be a steel pipe. They can make a relatively small opening in the very top of that, and now they mount the laser over it. They're not putting anything in that flow. They can read level and velocity without, again, having to do a lot of construction to make this work. So very easy to adapt to some of these applications. Okay, so Multipoint, this is a high-velocity site that was actually in Canada. You'll notice here it's meters per second, but this is 4.29 meters per second. We went ahead and we did a velocity. We set up, in this case, 3 points, 1, 3, and 5 for the velocity distribution. We could have turned on all 15. We chose 3 because the flow, even being as turbulent it is, was relatively uniform, but it is really moving. Some of the advances we made in the laser from day one was what we call steep slope focusing, steep slope mode. So if I have a very steep pipe, I may be working with an inch or less or, right in that range of level. Very difficult to read that. In the laser, we're able to set up the steep slope mode. In this case, it was a 15% slope, and now we were able to read very accurately the level and velocity in this line and give them accurate data for this type of high-velocity billing location. So incredible stuff. When you look at the actual flow data now, and I changed the units of measure so it makes a little more sense to us, but the average velocity of this line is 13.26 feet per second for this data that we're looking at. The scale on the left will show you that 14 feet per second, a lot of times they're almost pushing the maximum velocity of the laser at 15 foot per second. The level on the top pane in red shows you that your level is roughly 7 inches. We have 7 inches of flow moving at almost 15 foot per second. Incredible that anything can read that. But nobody's going to be able to install anything in that flow. Okay, so let's talk about some other applications. This is a wastewater effluent discharge. And again, we get that a lot because people want to measure that. There are a lot of flumes out there and weirs on wastewater effluent. A lot of times those are not accurate, and customers know that. They want a better way to do it. So we went ahead and put the laser in some of those locations. The key thing about this is that we are able to, with the diagnostics, see how much of the signal we're getting back with the laser spectrum, and we know if we're able to read it or not. So in this case, we were able to read very, very clean water, a little bit of turbulence here, a little bit of foam, and the laser did very, very well. Here's one that's a UV disinfection channel. More and more people want to measure the UV channel in order to more accurately dose or pace their UV system. In this case, we have a signature flow meter that is giving a 4 to 24 level, so they know what level is going on in that channel to maintain the proper level over their lights. The velocity, so they can control how fast it's moving to make sure they have the right amount of exposure time, as well as flow rate, so they can dose or pace the light intensity. So really the laser coupled with the signature flow meter is almost a UV disinfection RTU or controller. So incredibly beneficial in that location. Here's one that's a high velocity rectangular channel. This was not a good location to measure for any device, but you'll notice here the water is hitting the sidewalls and kind of crossing over. In this case, we did multi-point in order to pick up. Sometimes we did get good readings, a lot of times we didn't, so we were able to use the velocity distribution or profile in order to get good readings. To install in something like that, though, what's nice is that it's pretty easy to do. In this case, what they did, they just went ahead and they cut out an opening in the top of that grate, and they just set the laser right on that, and away they go. So easy to adapt in some of those applications. Okay, here was another application challenge. This is a drop pipe application. Happened to be in Istanbul, Turkey. I was out there. They wanted to measure flow coming out of this line. Nobody wanted to get in there. Very dangerous, very nasty chemicals in there. The first laser was not going to work, and the reason was because it was going to read level directly below it and then try to focus the laser into the bottom of the pipe. What we have done is we've done or designed a remote ultrasonic sensor, and what that does is now the ultrasonic itself is mounted up into the top of the pipe, so it can either be on a ring or in the top bolted to the pipe. It measures the depth in the same location now that it's measuring the velocity. So much more accurate method of reading flow, as well as compensating for some of these application challenges. This is one at an influent wastewater plant. You can see that the water is actually flowing out of that pipe and dropping into that the rectangular channel. Using the remote ultra, we don't care what it's doing in that location. It's able to read that application. This is a combined sewer line, and what they were doing here is trying to measure flow, which is sanitary on the baseline, was important to them. And because of the normal laser, ultrasonic would be reading straight below it, and it would have tried to focus the laser under the pipe, which was not going to work. Went ahead and we installed a remote ultrasonic up into that pipe, and now we are focusing the laser in the right location. So the laser in this application can read both a really low-level baseline flow accurately, as well as when it goes full pipe. So we see this again used in a lot of combined sewer outfalls or in overflows. This happened to be a relatively small one, but we do see some large CSO lines that they're still out there. So a good technique, good technology. Nobody wants to put anything in that flow. Okay, more and more applications now. We're seeing a change in the channel shape or angle coming through that manhole. This is not so bad. This is actually a relatively decent location, but they wanted to measure flow here. We have some cases where it almost takes a 90-degree bend in that manhole. Well, the standard laser in this location would have probably worked okay because it would use the ultrasonic about where that light, you see the light is, and it would focus the laser up into that pipe. But some of these are not so ideal. And in this case, what we've done is we were able to use the remote ultrasonic and mount it as it comes into that channel. The laser will now focus right where the ultrasonic is shooting, and we don't care what happens. In this case, it was high velocity. The pipe dimensions changed as it entered the manhole or went through the manhole, so the invert did not match the pipe dimensions. This is going to now allow the laser to be used in a lot of these applications that were very, very difficult, if not impossible, to read in the past. Okay, so let's look at some other applications. River monitoring, we see a lot more and more of that. Why do we see challenges there? Well, a lot of them will run low flow to raging rapids during storm events. What happens there, you got to put, if you do a in-channel sensor, you have cables to worry about. You also have some inaccuracies due to the type of technologies. You may have a sensor that will read very well at low end, maybe a foot to 2 foot deep, but will be very inaccurate at the high end. The high-end sensors might do well at the upper level, but not at the low end. So the benefit of the laser is a couple-fold. It can read both slow and low flow. It doesn't care really how slow that water is, and a lot of these can move very slow and can also be very low. But regardless of that, it can immediately adapt to high-flow situations. And because nothing's in the water, we don't have to worry about anything getting torn out. And it will be accurate throughout the entire range. So that's the real huge benefit of the laser is where it's looking, regardless of low level, high level, it will automatically adapt to those conditions. Okay, so here's a good shot of one that was installed. This is a site in Lincoln, and it's normally almost dry, very little bit of flow there. You'll see the laser mounted on that bridge. There's a sun shield on there, so any outdoor application we'd recommend a sun shield, and we use that to really for the ultrasonic level sensor part of it. But you can get kind of creative here. We did a little wrap that mirrored or looked a lot like the channel, so kind of camouflage it to keep the vandals away. Okay, here's another channel where we see a lot more on the west coast of the U.S., Southern Cal, Phoenix area. And what these are big, wide rectangular channels that normally flow, if they flow at all, a very small channel right in the middle of that big, wide rectangular channel. The challenge is, what are you going to use to measure this? Well, in the case of the laser, we can use a laser on a bridge. We can measure the flow level velocity very accurately right in that channel, upstream from where this little depression is, but we can measure it very accurately there. When the flows do pick up and now we overflow the sidewalls of that, we can use level to area data points to cover that entire channel shape. So the laser velocity in this case would be used to measure the center channel and again apply the level to area data points. It should be known that no, the laser is not going to read the entire width of that channel. And so if you really wanted to get a better reading, you might add 1 or 2 more lasers to the other parts of that channel. In the case of the signature flow meter, we can add that easily to 1 electronic flow device. Okay, slow velocity applications. More and more of these slow velocity lines we're running into. We talk about velocities that are less than ½ foot per second, again, are very, very difficult. Most sensors cannot read or distinguish from signal to the noise. That's very prevalent in clean water as well. Laser has a very, again, high signal to noise ratio. We can read extremely low velocities. In some cases, again, far below the specified 0.5. Each site will be unique, so I'm not going to say we're going to read it all the time, but you will know when you set it up based on that velocity diagnostic. Nothing I know of currently will read slower velocity than the laser. So here's a shot where you can see using a temporary mount. The laser point is in the water. That water's like glass, so very, very difficult application. In this case, what you'll see is the second pane there is the dash line is our spec at ½ foot per second. And we are reading far below even ½ foot per second. You'll notice we are reading down to, in that case, 0.39 feet per second. This one I wanted to point out. This is a wide channel, slow velocity going to the influent of a wastewater plant in Southern Cal. The amazing thing about this is the lowest velocity I've ever seen the laser read. The water velocity is 0.13 feet per second, which is absolutely incredible. All right, so how do we handle submergence? The laser, yes, is designed to handle submergence. Sorry to, if you're getting ready to eat lunch, I apologize for this picture. This is one where they know it's going underwater. They have a chain tied to it. So what does the laser do when it goes underwater? The laser is not going to read because nothing's moving where it's looking. But what we do is we have a continuous wave sensor that's mounted on the bottom of the laser sensor itself. So it has a built-in pressure sensor to measure depth. So now it will seamlessly transition from laser to this area velocity sensor when it goes underwater. So we have one continuous output for flow based on whichever technique or technology it's using at the time. This submerged flow condition has been very, very successful for us. Okay, let's talk stormwater. Stormwater applications. This one was one where they wanted to monitor. They weren't going to drill any holes. They used a couple C-clamps and just clamped the laser mount right to that. So it was very easy to install in a temporary application. This is that same site from outside as well as in the pipe looking out. If the flows aren't too deep, they can mount it inside the pipe, but you just want to be careful. If it's going to get deep, you don't want to potentially tear that sensor off. This is one that we call extreme stormwater. I call extreme stormwater. This is out on the East Coast. They were trying to measure this flow. This is a trickle flow moving at less than 0.2 feet per second, crystal clear water. They wanted to measure this flow, and the only way they were able to do it was using laser. So the laser is actually mounted up in that pipe, and you can see the laser point on the bottom that I've circled. The velocity moving very slow, and again, very clean water. This is a USGS project. They wanted to be able to measure baseline very accurately. This is the only thing out there that would do that low level, that low velocity. Here's some of the data from that. So what you'll see in this case is that level was 0.88 inches, less than 1 inch, and the velocity was an astounding 0.25 feet per second. So clean water, a crawl, and the laser was able to read that. So why does the laser work in these applications? Well, a lot of this I've already talked about, but we have a non-contact sensor. We use an ultrasonic to measure depth. It doesn't care what's happening hydraulically for the most part, like a wetted sensor would. It can be mounted exactly in the same location that you're measuring your velocity, which is ideal for flow accuracy. And really, the laser velocity, I can't stress it enough, the signal-to-noise ratio is phenomenal with the laser. So it's able to, again, distinguish the signal to what we don't want to look at. So incredible signal-to-noise ratio. Takes 5,000 velocity readings per point, does this in roughly 2 to 3 seconds. And we can do, up to 15 velocity points. So incredible flexibility as well as technology. Let's talk about some of the equipment options. So really it comes down to power. How are you going to power this thing? Is it AC or battery powered? What meter would I choose? If you're going permanent, more than likely you would use a signature flow meter. If you're going portable, you could go with signature as well, or you can go with the 2160. So in either case, we have a solution for you. The one on the right is the more waterproof unit. The one on the left gives you maximum flexibility as well as more of a permanent display keypad. So let's talk about signature a little bit. Signature is what we call a smart device. It can handle multiple inputs, up to 9 technologies coming into it for one electronics. But it can also output to a number of different devices: internet, alarming, USB, Flowlink, Modbus for SCADA, analog output as well. And obviously it hooks to a laser as well. So where we're seeing a lot of opportunity and solutions for customers out there would be industrial monitoring. This is one where more and more municipalities are looking for a better solution for their pre-treatment programs. One of the reasons why is because every industry has brand XYZ type flow meter, and they want some continuity between the data. So what a lot of these municipalities have looked at doing is using signature that gives them the ability to use an ultrasonic. If a customer has a flume and it's working and they like it, they can go that direction. If they don't and they want accurate data without that, they can go laser. Okay, so the nice thing about this too is it ties into Flowlink Pro. All the data gets pushed to a server that might be on the municipality's server, but the industry can now log in, and what they can do is log in under their own password the city gives them. They can see only what they are allowed to see. This is a dashboard view, so a customer can get an alarm saying, oh, wow, I have a high pH alarm, high flow alarm, whatever. They get a text message, they immediately pull up their phone, they log in, they can see what the municipality gives them authorization to see. In this case, green means everything's a go, yellow, we are not reporting in on the modem, and red would be we have a problem, hard alarm. A single click allows them to easily graph their site so they can see what's going on and make corrective action immediately. And we have GIS mapping capabilities as well. So for a large flow study or a flow project, a flow service company can have multiple sites out there. Quick glance, they can see what's going on in their system. All right, so we're going to wrap up. In summary, the LaserFlow is the most advanced and versatile open channel flow measurement system available on the market today. Like I said, I've been around the block. I've seen them all. I'm absolutely amazed every day that I look at data from the laser and what it's capable of doing. Because of that, it's able to work in applications that people in the past have said, there's no way to measure that. We're now able to measure in those types of locations. Accuracy was always in question with non-contact. Now we're able to give you assured accuracy with both high, low velocity flow measurement applications with non-contact. And when you have a wonderful non-contact device like that, having it available on the internet is very, very key, and we have all of that now as well. So really the LaserFlow is going to work in applications where other technologies would not. So with that, I'm going to open it up for questions. I want to thank you again for attending this webinar. I am Rick Dye, again, Global Key Account Manager. You can find me at rick.dey@teledyne.com. So if you have any questions or anything I help you with, let me know. We will now take some questions. So since we're on the web feature, we'd like you to go ahead and use the chat capability on that. Just go ahead and type in your question, and we'll see what we can do to answer those. If we can't get them all answered today, we will go ahead and answer those as we can and send those out. We are going to put this webinar on YouTube channel. We'll send out an email when this is posted, which should be early next week. Now let's go ahead. We're going to go on with our first question. Okay, so one of the questions, battery options. If I'm using a remote or a laser in a battery-powered location, what would I want to do there? Well, we have the 2160, which is the blue box, uses the standard battery module like a 2150, and you can either use that or you can add another battery module, depending again on how long you want to run this thing, depending on if you're using modems. We're going to get roughly about 12 weeks with no modem on a 2160 laser 15-minute reading. What I do tell people, though, if I'm going to run this long-term and I'm going to still be running on DC or batteries, what I would recommend doing is a deep cycle marine battery and maybe a solar panel. So it depends on where you're at in the world, how good a sun you have, but we can certainly assist you in designing that. Okay, so we do get some other questions on how accurate during a surcharge. Okay, when we go surcharge, we're using a continuous wave sensor. Continuous wave Doppler is very effective but does have a limited range. So if I'm in a 72-inch pipe, my flow depth gets deeper. Sometimes we can underestimate velocity on a standard area velocity sensor. With the way the laser AV sensor is designed, it's mounted on the bottom of the sensor. Now it's actually looking in where the more high velocity will be, and so the transition between the laser velocity and the AV velocity has been very, very close and very seamless. So it's done a really good job there. Okay, here's another question. I have 2150s. How different is a 2160 laser? Good question. 2150, again, we've sold thousands of those. There's a lot of those out there. When we developed the laser in the 2160, one of the things we wanted to make sure was that the learning curve or the transition to the 2160 would be very easy for customers. For those of you that have used the 2160, what you'll notice is they are almost identical in programming to a 2150. The only difference really is the velocity grid. So you'll see when you program a 2160, when you click on velocity, you'll have the 15-point velocity grid that you can choose. Otherwise, it's almost identical to a 2150. So the learning curve and the transition or the addition of 2160s to your fleet of 2150 is really, really seamless. Can we communicate with other communication devices? Good question. Another one we get asked out there. We have people using Mission, Telog, other communication devices. Obviously, we have our own communication, but if you are using other communication devices, we have a Modbus output that's standard with all of our flow meters using laser, so we can interface with those other types of communication devices. Just give us a call, and we can help you transition through that as well. Okay, how we relate a point velocity to the overall velocity or overall flow. What we use is we are looking for typically peak velocity, and it's a USGS thing where they've tested over time and found that if you can accurately measure the peak, the multiplier is a 0.85 to 0.95 multiplier. We chose 0.9 as our standard by default. So we will take and look for a peak velocity, multiply it by 0.9 to get the average. That has been very, very accurate in 96% of the applications I've dealt with. However, if somebody feels that that needs to be altered because of manual profiling or something different than the standard open channel 0.9, they can do some modifications to that correlation factor. Okay, here's one. Why would I use a LaserFlow over the standard area velocity in small pipes? And I've been asked that too. Sometimes people think that may be overkill. In some cases, it could be. It depends on what really your goal is. Depending on regardless if I have a small pipe or not, if I'm in a busy traffic area, a lot of safety issues, I can't get at the site, it's very difficult, you may choose to go with the laser just so that you can be assured you have no maintenance issues and no reason to have to go out, close off traffic, and clean a standard area velocity sensor. So laser is going to require very minimal, if any, maintenance. Speaking of that, another one was submergence rating. We rate ours at 6 feet, 72 hours. It's a standard IP68 rating. Having said that, I was just down in some place down south, I won't name them, but their laser was about 30 feet underwater, and it actually handled that quite well. So we far exceed even our own submergence rating, but I would not use this like a submarine. I wouldn't want to expect it to handle that all the time. So if you do have a site that's underwater daily, you probably want to go with a different technology. Okay, what sort of maintenance and testing schedule do you guys recommend? With the laser on the ultrasonic level, a couple things it does. It knows the distance to the water, all right? So when you install one, what you can do is you can take a physical measurement from the bottom flat spot of the laser sensor to the bottom of the channel. If that's 3 feet, for example, and the meter tells you my distance to the water is 2 feet, you know your level is 1 foot, okay? So you can write that down, and I recommend that at any time because that's going to be a more accurate method of calibrating the level than the ruler measurement. You're now getting a ruler measurement from the bottom of the channel to the bottom of the laser. We don't care that water might be splashing up on the ruler and so on. But the neat thing about that is once you write that down in your notes, the next time or anytime you post-process the data, you can look at the distance and make sure that your level hasn't changed. The velocity side of that, again, is the diagnostic stuff. When I look at the Doppler power or the velocity spectrum, I know without a doubt Nothing's happened to the sensor. It's reading very well on velocity. Again, the XY axis that's built into it will tell you if something shifted. So in the case of my buddies down south, when their laser was 30 feet underwater, once that water receded, I could see their XY axis did not change at all, which means I'm getting a good velocity reading, my XY axis hasn't changed, so the sensor physically hasn't moved, and my Doppler reading, my velocity reading is good. Don't touch it, don't go in there. Okay, what are the limitations to the ultrasonic sensor? 10 foot really is the only limitation to that. Okay, so we had an application where it didn't seem to seamlessly switch from open to surcharge. Okay, so in the programming there is a setting that we call combined flow or conditional flow. So what we do is we have flow rate for laser, we have flow rate for AV sensor. So what we will do is we will have what's called combined or conditional flow. And what that's set to is I'm going to use my laser until a set level that you program. So let's say I have a 36-inch pipe, my laser's at 36 inches. What you would do is you would say my AV sensor is 36 inches. That's the depth you tell it, even though it's not going to, water will not be up to the laser. You would say my transition point might be 36.5. You give yourself a half-inch transition. What it will do is, if you program it correctly, it will automatically switch from flow rate, which is laser, to flow rate 2, which would be your AV. But the output is a conditional or combined flow, which will give you one continuous output, either on 4 to 20, going to a SCADA system, or in the data storage. So if you have any questions on that and it didn't work, give us a holler. We'd be happy to help set that up, because there's probably just some confusion on some of the programming. So we'd be more than happy. Our tech support guys could help you as well. Okay, and with that, I think we are about ready to wrap up questions. Again, my name is Rick Dye. You can get a hold of me at rick.dey@teledyne.com. And we have a lot of questions. One last one, though. Go back to that one, if you would. Hydrogen sulfide. This is a good question, and then I'm gonna close it off for now. But again, Rick Dye at rick.dey@teledyne.com. Hydrogen sulfide. What level of hydrogen sulfide would affect the performance or effectiveness of the laser? Very good question. I can tell you we have lasers now that are in some tropical environments that have been installed now almost 2 years, and the hydrogen sulfide is so high their hydrogen or their gas meters will error out. I won't say where they're at, but in any case, they cannot get in those sites or do not want to get in those manholes very often. Hydrogen sulfide through the roof, lasers have been installed almost 2 years. They've never touched them, and there's been 3 of those in there. So I'm sure the laser sensor, some of this stuff might not look real pretty when it's pulled out, but based on the Doppler signal and what we see with all the diagnostic, nothing has affected the performance of it. They haven't cleaned it. They haven't done anything to it. So very impressed by how well it's been able to handle that. Okay, so again, I want to thank you for attending. We're going to go ahead and address all the other questions, or attempt to, that you've asked in a timely manner. As I said, we're going to post this to a YouTube account next week. And thanks again, and hope you have a great rest of the day or night, wherever you're at. Thank you very much.